Hi everybody and welcome back. We're continuing our Chapter 8 notes on work and energy, and this, which you might call maybe Section 2, is going to be on kinetic energy, and we're going to derive the equation for that, and then we're going to relate it to work and see how they are actually one and the same. Alright, so kinetic energy, as you probably know, is a function of something that has motion, has velocity. Alright, an object sitting at rest doesn't have kinetic energy. It may have potential energy, but not kinetic energy. All right, so something is moving, that means it has a velocity, right? And if you think back to kinematics, we have a couple of equations that that certainly deal with velocity. Well, we're talking about work, though, work and energy. And what's our equation for work? Well, work equals force times distance, right? All right, well, and something has velocity, you've got equations kind of like this right here. All right, v final squared and v initial squared and 2 times a times acceleration. Well, so what? Well, we want to link them together. We want to relate what we know about kinematics to forces. All right, so what is our link between kinematics and forces? That link is acceleration. That link is acceleration because acceleration shows up in both. We've got it right here, and we have it right here. Well, in fact, I'll erase this at the bottom for a second. All right. Well, let's take this, hopefully familiar to you, kinematics equation, and turn it around a little bit. So we're solving, at least mostly, for acceleration right here. By the way, if this doesn't look too familiar to you, maybe it's because you're used to seeing an F right there. V final squared is V initial squared plus 2 times A times, and you're also used to seeing a delta X right there where the D is, but they're both distances, they're both displacements, and so just another way of stating it. Okay, well, like I said a second ago, let's turn this around and solve that for acceleration. Put the final in there. All right, well, Newton's second law, that tells us that force equals mass times acceleration, and so as I kind of jumped the gun a little bit before, we turned that around to solve for acceleration. All right, so we've got acceleration here from kinematics. We've got acceleration here from forces. What we can do now to join them together and to link kinematics to forces and ultimately work is to substitute that in for A. So let's do just that. All right, we're going to go to the next page here. So if we substituted that statement about forces in for A, we now have this. Again, I'm going to write the final in right here. The final square, just so it looks more familiar to you. And remember that D is really a displacement or a distance that you might call delta X. But this is going to start looking a little more familiar to us, because remember that work equals force times distance. That's not a very good F right there. Force times distance. And so let's make a statement about force times distance and get everything else away from it. Okay? So we're going to multiply up that mass to both sides of that, up to the two values on the other side of that equation right there. And we're going to divide by 2, or you might say multiply by a half. So these 2's, well, there are going to be 2 2's that are going to come down in the denominator right there. So we have this. All right? We divided by 2 on both sides, and we multiplied by m on both sides. Well, that net force times distance, you probably know to be net work. And so we have net work equal to these 2 funny-looking equations over there. By the way, this is a final. Wherever you have a final minus initial, you might recall that that is a change in something, and this definitely is going to be a change in something. Well, what is this something? What are these values right here? Well, what they are is kinetic energy. Kinetic energy, and I usually write it as KE. You can write it as K if you want, but KE. Kinetic energy, the energy derived from the state of something that is moving, is described as 1/2 mv squared. Circle that, box that, put a dotted line around it, put stars. That is going to be important because any object that has mass and has velocity is going to have some sort of kinetic energy, and this is how to calculate it. 1/2 mv squared. It doesn't necessarily have a direction, it's just a scalar, it's a value, and it depends mostly on the speed v right here. Partly because objects don't usually change their mass spontaneously, although they can change their speed. And as the speed does change, look, the speed of the velocity is actually squared. And so let's say if you double your speed, what you're doing is you're actually multiplying your kinetic energy by 4 because that speed is squared right there. So as your speed changes, the kinetic energy changes exponentially because that velocity is squared right there. It has units of joules, and we're going to see in just a little bit how it's related to work. Because remember, work is measured in joules, which is 1 kilogram meter squared per second squared. Well, let's look at kinetic energy right here. 1/2. We'll leave out the 1/2 for now because it doesn't really have a unit. It's just a coefficient. Well, what do we measure mass in? Well, that's in kilogram or kilograms, right? And velocity squared. Well, velocity is meters per second, and if we square that, it's going to be meters squared per second squared. And that's exactly the same unit as a joule right there, which is what work is measured in. So we're going to see a little bit later how work and kinetic energy are inextricably tied to each other, all right, and how you can prove work is being done by the values of kinetic energy that an object has.